setup is complete, so let's welcome Christoph Hirche, who will be talking about hypothesis testing with differential privacy.
Okay, perfect. Thanks a lot. Thanks for the introduction, and thanks everyone for joining. Yeah, as you heard, I'm going to talk about hypothesis testing and differential privacy. And this is based on two papers. So you have here a graph of the authors. So this is Hao Chong, Cambus, Teshani, and Mark, who are all involved. And you see the two papers here, disjoint sets of authors. So we kind of worked on this at the same time, kind of noticed this last minute, and then decided to kind of publish it on the same day. And there's naturally a lot of overlap. So I'm kind of trying to convey you the story of both of these papers in this joint talk. And first, of course, I'm going to talk a bit about hypothesis testing and differential privacy as like the separate entities. And the first thing is hypothesis testing. So I guess this is basically the hypothesis testing day so far, so I don't have to give you much of an introduction to this. But I will nevertheless talk a bit about the beginnings, about the definitions, because there are some differences to the previous talks in terms of setting that we are looking at. So of course, if you followed the previous talks, you know this already. So the standard setting in hypothesis testing is you try to discriminate between two states. And this is all much simpler than, I don't know, the generalized quantum Steinslammer things in the beginning, because it's really just two states, there are no sets. You do a measurement, and then you try to guess which state you actually got at the input to your measurement. Okay? And what's a bit different here is that we are trying to look at the symmetric setting. So, put on the pointer. So you have here the probability of error. So naturally, there are two types of errors that you can have. One is to detect the second state when in fact it was the first one, and to detect the first when it was the second. And symmetric just means that we want to simultaneously minimize both of these errors. And the states appear with some priors, P and Q, which of course should add up to 1 usually. And that's basically our setting. It's well known that this error probability is described by the trace distance. And now we want to optimize essentially, or we want to look at the setting a bit more. And what we do a bit different is that we are not just interested in decaying this error, but we are more interested in the relationship between the number of copies needed to achieve a certain error. And this is usually looked at in terms of the sample complexity of hypothesis testing. So what I want to look at here is I want that the probability of error for n copies of the states is below a certain threshold, here denoted alpha. And now I want to find the smallest n such that we can achieve this. Okay? So that is basically the sample complexity of the symmetric hypothesis testing problem. Just in the setting, this is kind of reasonably well understood, and I kind of want to refer here to this, kind of almost like a review paper on this topic, so the sample complexity of quantum hypothesis testing, where pretty good lower and upper bounds on the sample complexity was given, mostly in terms of the Spear's distance and the fidelity. And in fact, these are the results that kind of are the starting point for our two papers. And I wanted as a remark is that since then things have been have developed a bit, and I wanted to advertise this result, which is actually in a recent update to this paper by Teshani and Mark, which gives kind of much cleaner lower and upper bounds on the sample complexity, where you can see, okay, this is kind of a quantity based on this Petz-Rainey divergence, so kind of essentially without the prefactor. And the lower and upper bound here are only different by a factor of, well, in total 4, basically. Okay, so you have a much cleaner bound. But most of what I'm telling you, because our papers are already a couple of months older, are based on the expressions on the previous slide. Okay. So that kind of covers the introduction for the first half of the title. So now we have the sample complexity of hypothesis testing. The second thing is that I promised to talk about differential privacy. Okay. So let's talk about differential privacy, and this comes foremost from the classical setting. Okay, I'll give you like a hopefully intuitive example what differential privacy means. And that is, imagine you have some database, and for example, the typical example that you have is a database in a hospital of patients that took part in a trial and they tested positive or negative for a certain disease or something. And now you as a researcher, you might want to run some analysis on this data and publish your results afterwards, okay? But obviously there's a lot of like data protection concerns. Maybe the individual patients don't want their data revealed. So what you demand is from the results that you publish, you can make a statistical analysis of these results, of the data, but you cannot infer if a particular patient tested positive or negative from for the disease or something that you tested on. Okay, and this is actually a fairly common framework, especially in classical information theory, machine learning, and privacy, and is used by Google and others to actually protect data in the internet. Okay, so how do you formalize this now? And here I kind of skip a couple of steps and give you like directly a very convenient definition or a very convenient test, how you can see if an algorithm is differentially private. And formally, we define an algorithm A as epsilon delta differentially private if the hockey stick divergence, I get to that in a second, between the outputs of the algorithm for two different input states is smaller than delta. Okay, these are here the epsilon and the delta. Those are kind of these parameters. The epsilon is kind of the flexible one. You can have kind of a choice what you put here. Delta usually needs to be like really information theoretically small in some sense. And you have the supremum over rho and sigma, which are usually just chosen to be neighboring states. Okay, now you're in some sense very free to decide what neighboring means. In the classical case, you would often go for something like the Hamming distance or something, and just really have the difference in a single bit, like your databases should be equal except a single bit. This hockey stick divergence, I defined it here on the right. It's basically, think of it as a trace distance, just that I introduce this additional parameter gamma here. And it turns out that this has exactly this interpretation of this differential privacy problem. Okay, the hockey stick named after how it looks when you plot it. Okay, so this is a general framework or the beginning framework of differential privacy. But in this talk, we look at a kind of subclass or a particular class that is called local differential privacy. In local differential privacy, now you imagine that your data is not local, like it's not in like one data set that is somewhere in a fixed location, and you want to distinguish between different bits or like changes in a single bit. Oh, where's my here? But now you kind of think of your database as distributed between a lot of parties, and what you want to accomplish is privacy for a particular party in this network. So now you're interested not just between neighboring states, but in your definition, you input all possible states, which at first seems like an unreasonably strict criteria for defining this local differential privacy, but you should really think of it as guaranteeing full privacy for one party among a large set of parties, and that's why it's called local differential privacy. One comment on this, which is actually very nicely proven in the paper by Tishani and Mark, is that we kind of want here to look at, or we want this for all states rho and sigma, but it's in fact enough to do this for all orthogonal pure states. Okay, and yeah, that's something Mark and Tishani prove in their paper. And this equivalence makes actually a lot of the proofs in the following much easier. So now we have the sample complexity, we have the local differential privacy, and now we want to bring both of these two things together. So we define kind of a sample complexity under privacy. And okay, these are basically the definitions. So what do you have here? You still, okay, first we define the sample complexity under noisy channel A, and that's basically the same thing, just that now your inputs run through this noisy channel, and then you get n copies of the output state, and these ones you want to distinguish with an error probability smaller than alpha, and find the smallest n such that this works out. Okay. Now, if I want to find the sample complexity under differential privacy, I take all channels that give you differential privacy, and I take the smallest sample complexity, so kind of the best case scenario, under all these differentially private maps. Okay? And I want to compare this to the usual sample complexity and see how much worse kind of my results get if I demand this differential privacy criterion. Okay? And I kind of jump basically right to the end, and I give you kind of the results. So this looks like a unnecessarily complicated theorem with a lot of lower and upper bounds. But this is mostly because, okay, I'm presenting like these two separate papers, right? So they kind of have a lot of different bounds, and it's not necessarily that clear which ones are, or they're not necessarily always perfectly comparable, so you just decide to put all of them here. But the important thing is kind of that the lower bound is usually that mirrors exactly what you have in the classical case. So in the classical case, there's quite a tight solution where you get this trace distance squared in the bound and some prefactor on depending on epsilon, like this privacy criterion. And the lower bound, you actually have some kind of, it's almost in the best bounds that we have, there's almost this kind of phase transition where for a large range of epsilon and the probability, the error probability, this alpha, the optimal lower bound is governed by the trace distance, and at some point it kind of switches to being governed by this Hellinger divergence, and I get to the Hellinger divergence in a second. Okay, so these are basically the results, and now I want to kind of talk a bit about how to get to these results. And I think this is actually kind of the kind of, yeah, almost the more interesting part of this talk, because we talk about a couple of tools that are not just interesting here in proving these particular results, but possibly have a bit of a wider application also. So let's talk about a set of tools that in the two papers were used to come up with these results. And this is inequalities between divergences, contraction coefficients, and then kind of new types of reverse Pinsker type inequalities. Okay. Doing on time? Okay, I think that's good. Let's start with the inequalities between F divergences. So here we take a particular type of F divergences. So these were defined I guess by now almost 2 years ago by Marco and myself, these quantum F divergences, which are based on the hockey stick divergence. And you can already kind of tell that this is a very natural definition if I want to look at anything that's related to differential privacy, right? Because if you take any of the usual definitions that you might know, you need to do a lot of work to kind of relate them to the hockey stick divergence, but here it literally comes in the definition. So you kind of save yourself a lot of effort in some way. And it turns out that a lot of the things that we need to prove work extremely easy with these ones. To give these divergences a kind of more familiar form, you can plug in a particular function f. And if I choose this function x to the power alpha with some additional constants, then I get something that is a Hellinger divergence. Okay, if I choose alpha to be 1/2, then that is exactly the quantity that showed up in the first lower bound on the last slide. But related to a maybe better known quantity, these Hellinger divergences are in one-to-one correspondence to the Rayleigh divergences. Okay, and these you have seen plop up at several points in the previous talks. So now, kind of what is one of the first points where like using this particular F divergence helps us a lot in proving these relationships, where one is that you can use this representation to prove inequalities between different divergences. And in particular, what makes these divergences nice is that the function f and these hockey stick, or the part where the quantum states are completely separated. Okay? So if I want to prove an inequality for these divergences, I can do that essentially by just looking at the function f to relate it to a different divergence. In particular, I can just bound the two derivatives of two functions by each other, finding like a good constant c such that these inequalities hold, and I prove new inequalities that way. Okay, it's quite, I guess, intuitive, quite obvious. And if you choose these functions in a smart way, what you can, for example, find is that a particular instance, these Jensen-Shannon divergences, can be directly related to these Hellinger divergences. Okay, and that then immediately implies bounds for these sample complexities, because I can kind of give the sample complexities with a quite simple Pinsker type argument in terms of these Jensen-Shannon divergences, and then I can now bound them in terms of Hellinger divergences. Okay, and why is kind of this proof technique? I don't know. It's actually kind of one of my favorite examples of using this particular way of proving something, and that is because even in the classical setting, I think using these integral representations is kind of underappreciated. So the idea of even coming up with proving this kind of inequality stems actually from a classical paper that proved kind of optimal rates of sample complexity for hypothesis testing. But they used an extremely complicated proof to do that. Okay? And they came up with something that in the end turns out to be like a factor 40 or something worse than this proof technique. So it's kind of, yeah, I think it's kind of a nice story that using these integral representations does not just improve or just doesn't just give you new entropy inequalities in the quantum setting, but it also gives you much tighter entropy inequalities in the classical setting. Yeah, this kind of just remark how this is used. So if I want to find on the n that is like the optimal n for the sample complexities, I can quite easily lower bound this in terms of the Jensen-Shannon divergence. This allows me to bound this in terms of the Hellinger divergence, and it's also you can prove an upper bound as well, which kind of means the sample complexity can quite tightly be described in terms of these Hellinger divergences. Okay, and that's kind of the starting point where now you're kind of trying to bring in differential privacy. The second tool that is important in this context is to look at contraction coefficients. So let me briefly go over the idea of like using contraction coefficients in this setting. And here it's kind of, okay, what are contraction coefficients? They're kind of just strong versions of the data processing inequality. I guess everyone's kind of familiar with data processing, right? But often we want something stronger than the typical data processing inequality. And that is we introduce an additional constant here that, that kind of is hopefully strictly smaller than 1 and hence gives us a strictly stronger inequality. Okay? And these constants, they can be derived or they are kind of simply defined as either just a supremum over rho here, in case we just care over a variable of sigma. And these are usually called the strong data processing inequalities, or the corresponding constants. And if we also want it for like all sigma, then we optimize over sigma, and these are called the contraction coefficients, right? So they're really just the optimal constants that I can just always put in these data processing inequalities to make them stronger. Particular example is, for example, I can do this. So here I kind of these big D's, they're kind of generalized divergences, but a particular example is, for example, to do this for the trace distance, for which, in fact, you can even get a simpler formula because these are optimized by orthogonal pure states. And the same kind of holds, for example, also for these hockey stick divergences. So there you can kind of connect them back quite easily to the differential privacy setting. Okay. Now these contraction coefficients, you can define them for all states, but here in particular we are interested in what is like the maximum contraction coefficient if I allow not just for all inputs, but actually I allow for all channels that obey a certain criteria. Okay. And in this case, we want them to be all channels that are epsilon differentially private. So simply the ones where the hockey stick divergence for some particular parameter is 0. And this gives me additional constraints on these contraction coefficients that I then can try to calculate basically, or to at least find bounds on. the natural kind of definition here is, for example, to use the hockey stick divergence, which is, okay, literally the definition, right, with the hockey stick divergence. And this kind of turned out to be the crucial tool, because what you're essentially trying to do now in proving this differential private sample complexities is you're trying to remove the channel n by just getting like some prefactors, right? And these prefactors are exactly these contraction coefficients. So you just need to find out what are the optimal values for these contraction coefficients under differential privacy. And yeah, you can actually look up both of the papers and find a couple of results on these. And I think in our paper, we kind of just did the necessary things to prove these sample complexities, but actually Mark and Tashani went a couple of steps further, and they kind of tried to find the most general and tightest relationships, and they actually gave equality conditions for those. So you probably want to look up their paper if you want to see the optimal values of really these contraction coefficients under differential privacy. And okay, I guess I have like 4 minutes, so this should actually work out fine. The last tool I want to talk about is these reverse Pinsker type inequalities, and that's another thing where these particular shapes of F divergences come in quite nicely, that you can kind of reformulate this all in these F divergences. And this is actually, from the techniques here, I would say this is largely based actually on this early work on these contraction coefficients, on these F divergences. So again, back to the paper that Mark and I wrote some time ago, where you can give reverse Pinsker type inequalities. So by that, I mean everything that upper bounds the divergence with some prefactor in terms of the trace distance, okay? And you can kind of guess already, if I have these types of inequalities, those give me exactly the trace distance bounds in the sample complexity, okay? And it turns out that these inequalities are actually tied. So we can actually give like kind of the perfect reverse Pinsker type inequalities if you apply this differential privacy setting. And these are kind of, the proof technique is essentially just that you take apart these integral representations of the F divergences, you bound the hockey sticks with the differential privacy condition, which gives you a lot of like Dmax quantities that then under differential privacy just give you these epsilons. And these reverse Pinskers are actually even the classical setting, the tight inequalities in that case. And yeah, I'll just put here kind of what is the outcome kind of when you use this. So for example, if you apply this to this H1 half that is the lower bound in the sample complexity, you get exactly these prefactors that you need in terms of kind of comparing it to the trace distance, okay? So this is kind of the list of the tools that you might want to take away from these projects in order to kind of bound things like sample complexities under the influence of noise. And there's just like an overview. So yeah, we'll have these sample complexities under differential privacy. And the tools that you might want to take away are that you can find like new entropy inequalities, you can find new bounds on contraction coefficients and reverse Pinsker type inequalities. And I think that's basically everything I had prepared. So thanks a lot for your attention.
Thank you for the nice talk and also for keeping track of the time. We have time for questions. Is there any?
Sorry.
Thanks for the talk. So I'm wondering whether you can recover the Stein's lemma from the expressions with the
sample complexity.
With the sample complexity. I didn't see it directly, but it should be from changing this P and Q that you see the relative entropy, but I didn't see the relative entropy, so that's why.
I think in this case you cannot directly get the Stein's lemma back, but you can look at sample complexity in an asymmetric setting as well, right? And I think then it's a dual problem, right? So instead of fixing the n and optimizing epsilon, you just do the opposite. So I don't know if you can directly get back. I don't think so, but it's just kind of the dual to the sample to the Stein's problem, kind of. Yeah. I think there's one.
Very nice talk. I like all the various inequalities. The one thing that I was confused about is operationally, how would one actually translate this to a system? Can you give an insight on that? What you think? I mean, you had a example about Google and such using this kind of stuff, but nothing concrete. Could you give an example which is concrete? Sorry for putting you on a spot there.
I see. So I think in a classical example, it's quite a natural thing to look at. So it's very, people use it like in machine learning for robustness bounds and so on.
Example, quantum.
Well, actually, if we want like a very practical example, right? Google uses this in Google Maps, for example. If you look up on your phone, you see these statistics where you go to a place and it tells you currently it's very busy or something, right? You get these graphs. And essentially, that's one example where Google uses differential privacy as a model to tell you, I mean, to kind of prevent you from tracking individual people. I guess this would be very coarse-grained anyway, but it's like the typical example people name. The other thing is kind of in machine learning, people use it to prove robustness. So, like robustness of a discrimination protocol, for example. They use it kind of to show that if you alter your input a little bit, then the output won't drastically change. And that's kind of the definition of robustness of a discrimination protocol. So differential privacy can give you bounds on that, like provable robustness bounds. If you're asking for an example with quantum states, that would be much more harder.
In your case, so what you have is you're trying to discriminate. You had a collection of channels versus a different collection of channels. Your discrimination problem is in itself a problem of that the adversary is actually trying to solve as well. I mean, I think that the solution is very clever, but it would be nice to actually have a very system-oriented slide, maybe like this is what we're trying to do, and that's how we're doing it. So I think you conceptually it's understandable, but how it's actually done is not connected very well. We can talk later.
Okay, let's do that.
Seems there are no
good.
questions, so let's thank the speaker.